Sorry, I had some technical problem actually. So we start again. Wait. So okay, we were here. Until here. Okay. So now we know what is the outer diameter of our coaxial line, which is 3.44. So our inner diameter is 1 mm and our outer diameter is 3.44 millimeter. So from the other equation that we have actually demonstrated before, so we know all the values here. So we put the values and then we estimate our maximum frequency. So we have here, and it seems that it is 25.8 gigahertz. No problem. And then we put all the values on this equation again, or you can choose this equation, it's up to you. And then by doing so, we get this 3.64 dB per meter actually, but our cable is 50 meter long, right? So we just multiply and then get the answer. So this is how easy is this one. But however, sometimes in exams or in test, things can be twisted, so you need to understand these basic principles, and if you understand the basic principle, the twist will be not difficult for you, inshallah. So the coaxial cable is done. Now we move on to the strip line. Okay, so strip line is a little different estimation than the coaxial lines. In strip lines, to find the Z0, the equation is this one. It's from the book actually, in 3.179a. So in book Poser, 3rd chapter, and equation number 3.179a, you will find this. All these are actually from the book. So this is how you estimate. Now ER we know, this is dielectric constant, and B here is the height of the dielectric. Okay, it's in millimeter, it can be in meters also. Now what is WE? Okay, WE is basically the effective width of this. Our goal actually basically to find this W. Okay, for any strip line or microstrip line, our basic goal is to find W of the line, means the width of the strip line. Okay, but to do so we need to find we need to find WE. However, WE sometimes mainly related to estimate the characteristics impedance of the line. If the W is given, then from here actually you can estimate WE, and then from WE you can actually get the Z0, means the characteristic impedance of the strip line. So now what is W? I already told you the W is actually the width of the strip line. WE is the effective width of the strip line, which can be used to find, is in this equation to find Z0. So remember one thing, that there can be conditions, if you don't know how to read this equation actually. Okay, I make things easy for you. The condition is nothing but like this. Let's say that W and B is given, okay, which is less than, let's say W is 1 and B is 2. Okay, so if it's like this, then what will happen? This we will choose. Let's say W is 0.35 and B is 1, so it's 0.35, right? So we choose this one. If we choose this one, then this goes away. It's something like this. So for this situation, W is 0.35 and B is 1, or 0.3. Let's say W is 0.3. If W is 0.3 and B is 1, so this value comes total 0.3, right? So if 0.3, then this actually condition satisfies, and if this condition satisfied, then only 0 comes here, minus 0 means WE by B is equal to W by B minus 0. So only W by B is equal to WE by B. It means WE becomes W, same. However, if this becomes bigger, let's say W is 0.5 and B is 1, so this is bigger than this, right? So then this will satisfy, which is here. So we need to write like this. So we take this one and we replace it with here. So WE by B is equal to W by B minus the whole thing, and then we put our W by B value, and then we estimate this one. Then we will see, we will find WE and then we put it here. That's how the Z0 actually estimated. Now if the Z0 is given, then what we will do? Then we need to estimate W. So it's like this, same thing basically, but remember Z0 is given and ER is known to us. So first we're going to do what we're going to do. We're going to multiply this one and check that this is 120 or not. If not, then we take this. If it is, then we take this, same as this one. Okay, I hope that you understand already that how to read and how to fix these equations. Now if W by B is equal to X, then X is equal to, this is from the book also. So that's how the estimation can be done. Now one more thing, that we need to estimate loss. Here in this case we need to estimate WC, same way, root over ER. If it's bigger than 120, it's less than 120, then we choose this. If not, then we choose this. However, there is one A and one B, you see here, which is given here. Okay, so we have to be very careful. Okay, only for this, remember, once we find our W, then we can proceed into this one. Okay, because we can estimate our W here first. Okay, and then we move on to this one. Then we find A or B, whatever is condition necessary. If the condition this one satisfies, we need to find A. If this condition satisfies, then we need to find B, and then after that we need to estimate alpha C. Alpha C means basically the conductor loss, and then the dielectric loss is this one. So we move into our example. So the example says that find the width of the, so remember we need to find the width, this width. Okay, so we need to find the width for 50 ohm copper. So it's given 50 ohm copper, characteristic impedance is given, Z0 is given, strip line conductor with B is given, ER is given, and the loss tangent is given, and the operating frequency also given. So we need to find the attenuation, and the conductor thickness is T is given also. Okay, no problem. So our estimation first is the width estimation, no problem. We go for this first, this check, we check this first, which one? Okay, so we check here, we multiply ER with Z0. If we multiply this, then we find out it's 74.2, which is less than 120. If it's less than 120, so this is W by B is equal to X. So X is equal to this, so we're gonna find it. So this is equal to X and this, and then we find value of this one, and so on and so forth. W has been estimated already. Okay, now since the W has been estimated, now we need to calculate the attenuation, means the total attenuation. Okay, so total attenuation is basically let's basically alpha C plus alpha D. Okay, now we need to find first the alpha D. We need to find K first. We know from the equation twice pi F root over epsilon R by C is equal to K. So we find K like this. We have all the values, just need to put it and calculate by calculator, and then we have already alpha D, which is, remember, this one is Napier per meter, and this tangent delta is given as 0.00 1, which is known from the here. Okay. Now remember one thing, that you always need the surface resistance to calculate C, alpha C. Okay. If it's not given, then you need to ask your lecturer that why it's not given. By the way, remember, possibly it will be always given to you. Okay. If not, either you can ask your lecturer, or you can remember this one, because this is copper, is like commonly used in PCB. So RS for the copper is actually a constant, so which is 0.026 ohm. Okay. So you just memorize this one, will give you a lot of ease. Now we need to find, remember, I will not calculate A or B or C for you. You know, these things you need to calculate. Okay. Since the first criteria has been fulfilled, so we need to go with this one, and then A you need to calculate by W, B, pi, and these values you need to put, and then you need to put all other values to find out this. Okay. So this is your job to do. So until here we are done. So now we have alpha D and alpha C, so we add. Okay. So here now there is an important conversion here, that from Napier per meter you need to convert it into dB per meter. Okay. They have given you something like this, but however I put it here that 1 Napier means 8.7 dB per meter. So you just multiply with this one, you will get this value. Okay. No need to understand this one. Now we have per meter value, right? Isn't it? Per meter value. Now we need to find out how much is the wavelength, because it have given you the dB per wavelength, right? So we need to find the wavelength in meter, and then we multiply that one with the per meter value, will give us the value of the total loss per lambda. So we need to find the lambda here. So lambda is equal to C divided by root over epsilon RF. From there we get in centimeter. Since we know that this is meter value, right? So we need to divide this by 100. Okay. Once you divide by 100, you get this one, and then we will multiply with this, will give us the total dB per lambda value. So it's as easy as like this. But remember one thing, it's very, very big recommendation from my side, that these solutions can be very, very long. Okay. And very, very confusing sometimes. If you don't practice, you will be trouble for sure, 100% trouble if you don't practice. Okay. So that is my recommendation. So now we move on to another segment, which is microstripline approximations. It is little different than the strip line, where you need to find one extra element, which is called the effective dielectric constant. Okay. So alpha epsilon r will be given. From there you need to find the effective dielectric constant. Okay. If W and D is given, or the ratio between them is given. So similar, actually in same way that what we have done so far in the strip line. First, if W and D is given, then you can estimate your Z0. How you gonna do it? You need to first check that W, if the W by D is equal to or less than 1, then you choose this one. If not, then you choose this one. Okay, that's how you gonna do it. However, there can be a question in both microstrip line or strip line, that if they are equal, okay, then if you are equal, I would recommend you to go for the easy one. Okay, let's say this is easy one, right? So you go for the easy one. Now, if W and D is given, then you can easily estimate this one. Okay, so I will not go so deep inside. But however, if Z0 is given, and then you need to estimate the W by D, or W you need to find, then this is the way to do it. Now this is the same drill, basically the same drill, where W is the width of the strip line and D is the height of the, sorry, it's not a strip line, actually this is a mistake I have done. Okay, it should be microstrip line. However, it's no problem. let me fix it. Later on I can okay, so I have fixed it. It's supposed to be a microstrip line. Okay, so here we were here that we need to figure out for microstrip line. Basically, that's a little bit tricky, but it's not so tricky that you cannot do it. Okay, it's like this, that if we want to estimate this one W, then D is given and Z0 is given and other ER is given. First you have to assume one solution. Let's say that you are estimating this one, and first you assume this, that okay, W by D is less than 2, and then you try to solve it. If you can find that W by D is less than 2, then your solution is right. If not, then the whole solution is wrong. So inherently this solution will be right for you. So you have to choose this solution and then you need to find your D. However, once we go to our problem, then you will understand more. Okay. So now since you know from the strip line, actually basically, that A and B, you need to calculate also, but here A and B is different than those A and B. Okay. And then we need to estimate the dielectric loss and then the conductor loss, and then due to these things, the basically the design will be finalized. Okay. Here there is one example. Okay, this is the last example actually in this lecture, and with this example we will conclude our this session. Here it says that design a microstrip line on a 0.5 mm alumina substrate, means this is height is given. Okay, ER is given 9.9, and the tangent delta is given also for a 50 ohm characteristic impedance, means the characteristic impedance also given. Okay, so find the length of the line required to produce a phase delay of this. Later on we will discuss about it, but first we need to design a microstrip line, which is basically, design means the W and D. We need to find the W. D is given. Okay, so we need to find the W. Okay, so our initial guess is this one. We go back here again. Here our initial guess this. Okay, that we will choose this solution. No problem, we go back. If our initial guess is this one, so we have this. Now we need to find A. A is, when you're gonna put these values, you will get this one, right? Now if you put this value here, e to the power A, and these values, you will get something like this, which is actually the initial guess is actually right, means it is less than 2. See, it's 0.9. If by any means if it came around 0.001, then this is gone. Then you need to choose this one where you have this, so you have to calculate this one. Would have been calculated this one actually, but in this case it's not. We got already this value, and then when we choose this case, then it's actually valid here. Okay, if not valid, then you have to choose W by D is greater than 2. Now you can ask me that if in between means W by D is equal to 2, then I would say that you go for any of them. It's up to you. It's your choice totally. But rarely you will find something like this. You will find, then well you show me, it will be a very rare case. Okay. Now we are here. We already have estimated our W, right? W by D. So from W by D, we know D is 0.5 mm. So we have W is equal to 0.483 mm. Sorry, that I forgot to put the value of the unit. Okay. Okay. Now our W is done, means our design is done. but the question is also expanded, that asking you to find the length of the line required to produce a phase delay of 270 at 10 gigahertz. Okay, no problem, we solve it. To solve it, we need to find this L actually. Okay, L, where phi is equal to total, basically phi is equal to beta L. Okay, and if the phi is equal to beta L, but beta is equal to root over epsilon E K naught. So epsilon E we need to find. So from here we find 6.665, and this one comes here. Okay, from K, if you want to find K naught, then twice pi F by C we know. So we got it, K naught. Remember, K naught and K is different. If it's K naught, then there is no dielectric constant here. If K naught, then there is if K naught, then there is no dielectric constant. If there is K only, then there is supposed to be a dielectric constant here. Okay, now for L, we put the values, all the values here. So phi L is equal to phi divided by L is equal to phi divided by root over epsilon naught K naught. So K naught value we know, and epsilon naught we know, and then this one. Okay, this is in radian. Okay, this, because this is a degree, so you need to multiply this one to make it radian value. So we got it 8.75 mm. Now the length of the line is known to us. Okay, so we know, and compute, we need to compute now the total loss on this line. Okay, so this is another answer is done, this part. So now we need to find alpha D. Alpha D is from here. So you put all the values, you get alpha D, and you put all the values here, you get alpha C here. So alpha D is, first value we get is 0.255 Napier per meter, which is actually 0.000255 Napier per millimeter, because this is per meter, right? So you need to divide it into 1000. And then see what I did, from here I converted to dB. So Napier multiplied by 8.7 give us Napier per dB per millimeter. The same thing I have done here. Alpha C is equal to 1.08 Napier per meter using this equation. And then I have divided into 1000 to bring it to Napier per millimeter, and then I multiply this whole thing with 8.7 to get the dB per millimeter, and then I added the total loss per millimeter. Okay, the total loss per millimeter. This is a mistake I have done. I think this is supposed to be millimeter. Okay, so total loss per millimeter, remember this one. This is a mistake from my side. Then since we know now that what is the total loss per millimeter in dB, now we need to just multiply this total length of the line to get the total loss in the line. So the total loss in 8.75 millimeter long line is this multiplied by this is equal to 0.101 dB. So this is the answer and the finalization of the 3 different examples that we have done. We have done the coaxial cable, we have done the stripline design, and then we done the microstripline design. That concludes our lecture. This is an attendance assignment for you for lecture 4. So here I will open up a link inshallah for you to submit. Thank you for your patience. Assalamu alaikum wa rahmatullahi wa barakatuh.